Okay, that was the end of my talk. Thanks for listening. Okay, so I'm Thomas Wolf from Hugging Face. We're doing conversational AI, but also open sourcing. So if you're doing NLP, you may have seen our products, which are actually based on transfer learning. So that's what I'm going to talk about today. I'll start from the concept, show you tools, focusing on our tools, and then some words about language generation. So this is the overview to get you all on the same page. Concept, as I said, what is our transfer learning, because maybe you're not all familiar about it. Open source tools, application to language generation, and some words about using that in production, because that's a huge focus we have to. Some slides from this are adapted from a tutorial I gave at NACL with my awesome collaborators, Sebastian Ruder, Matthew Peters, and Swaba. That was earlier this summer. So if you want more details, just go on these slides. There are like 300 slides with hand exercise, coding exercise, everything. So a lot more than what I'll be able to cover today. So what is transfer learning? So transfer learning has been a huge revolution in NLP over like the last 18 months to 2 years. Okay, so it's pretty recent, but it's like changing everything in the way we design our models, and also in the leaderboard, basically. So the traditional way that you've probably just heard a lot about also in the previous talk, which is the way we usually do machine learning. So when we have a first task, we gather data sets, we initialize a data-driven model. So this is all about data-driven models, right? We initialize our models with random weights, and we train on it to get the best performances on our task. And now when we have a second task, we do it again, okay, right? We gather another data set. We're starting again with random weights initialized from the model is initialized from scratch, and we train the model again. And if we have a third task, same thing again, okay? So it's a bit stupid, right? We humans don't do that. When we have a new task, we're not like forgetting everything we've learned before. We're like reusing that so we learn faster, and usually both at the same time, we also get better performances, okay? So transfer learning is one way to try to do that in machine learning models too. So the idea is that we have a bunch of source tasks, can be just one, can be two, can be a lot of them, and we train a model on them, and then when we have a new task that come around, instead of starting from scratch, we try to start from the knowledge we've already gathered, okay? Which definitely makes sense. And there are two ways to do that. Oops. No. Okay, sorry. There are various ways actually you can do that. You can train on all these tasks at the same time, or one after the other. And the thing I'm going to focus on today is what is called sequential transfer learning, in which you first do this pre-training, and then you do the adaptation here. So pre-training means you will train a model on a task that may not be the one you want to use at the end, but which is like a task on which your model will learn useful knowledge and patterns. And then adaptation is a second step of training, in which you will focus on your target task, okay? So the sequential training approach will have basically two main building blocks, if you want to see what's inside. The first thing is the model, okay, that you're using. So this model may have two architecture, one architecture during the pre-training, and then one architecture during the adaptation. So they might be the same architecture, but you may also change some stuff during the adaptation. I'll show you some examples. So there is a clear trend right now toward using larger and larger models for pre-training. So we pre-train here these models which are larger and larger, mostly based on transformers. I'll show you a little bit how it is. One exception is ULM-FIT, which is a RNN, well, actually LSTM, which is also working quite well for simple classification tasks. But mostly we use transformers because these models can really leverage huge data sets. They're quite efficient in the way they are trained because they are trained non-sequentially. And we can really scale them to huge data sets, and they can make use of this huge capacity. And then for the training itself, we also have this, obviously these two kind of settings. One setting during the pre-training, in which we are training the model on one data set, which is usually very large and unsupervised, and then another setting during the adaptation, in which we are training on our target datasets, which is usually very small because that's our own annotated datasets, and which is really task-specific. Okay. So here the main trends are that the pre-training is done on bigger datasets with very long range dependencies. So we train on full books, full Wikipedia articles, full Wikipedia pages, and this helps the models learn long range dependency. So how are the models mainly? They are transformers models. So they are like this. Basically, it's very simple models. We just convert our words in the words vectors as we usually do. So this is a sequence of words. We convert that in a sequence of vectors. Then we have a step of attention in which we actually mix these vectors together. We have this, which is the nonlinearity, which is the usual nonlinearity in a neural network, so that it just doesn't reduce to a linear model. And we have a series of blocks like this. So when we have a very big model, it just means that we have like 20 blocks like this. They're all the same architecture. And the main difference between all the models that you may have seen, which are all these very large-scale models, is the way they are trained, is the objectives that we set up. For some of them, like the famous OpenAI GPT-2, it's causal language modeling, which means the model will learn to predict the next word given the previous words. And for some of them, like BERT or Roberta, it's mask language modeling, which means we'll mask some words in the input sequence, and the model will try to rebuild these words from the context. Then when we have trained this model on our pre-training task, we adapt it to switch to target task. Usually the general workflow is very simple. We remove the last layer if we have a special layer for our training task. It can be just a softmax that we use for our language modeling. And then we add some layers that will be useful in our task. It can be very simple, just adding a linear projection on top of the model to project it on two tasks, if we want, on two classes, if we want to predict, for instance, two class, like predict something is true or false. We just add a linear layer that projects all the vectors here just to log it. It can be very complex for complex tasks. For instance, if you have trained a model on language modeling on one language and you want to use it for translation, you have to switch for these two languages. Then you will have to initialize as much as you can from the pre-trained weights, but you can't initialize everything. So you can have very complex adaptation, but it depends on what you're doing. Why do we use this kind of language modeling, this, what I was saying, this way of predicting words? Because it's actually a very general task. Predicting words is one task that doesn't require a human annotation, so we can just feed it every text we want. We don't need to annotate it. And it's also a very difficult task. Here is an example from BERT, which is provided with the beginning of a sentence that say, I think this is the beginning of a beautiful, and then it has to predict the last word. There are many possibilities here, and you see that these are all the top 10 probabilities from BERT. And all them kind of make sense, right? It can be a beautiful day, beautiful life, beautiful future story. So the model has learned to predict some kind of common sense here, some kind of logical way to end this sentence. So it has to learn syntax, semantic, all these to be able to select only the most relevant words at the end. So how do we adapt a model that's trained like this? So this is when we train it on a simple text classification task here. So TREXIS is just a text dataset with 6 intent to classify. So we have input from our customers, for instance, and we have to predict if it's like a description of the product or if it's something like that. That's just simple text classification class, okay? And the cool thing, as you can see, is that it goes really fast because the model starts from a very good training point because it has been pre-trained on this huge data set. In just one epoch on our data sets here, in just one epoch, we already have an error rate which is lower than 10, so we only have over 90% accuracy. So these models are very data efficient when you want to fine-tune them. The pre-training is not, but the fine-tuning is super data efficient, and you have also very, very high performances at the end. Here in this example, we have the state of the art on these data sets. Now, how can you use these models? They are very costly to pre-train because we pre-train them on huge data sets. So you should probably use open source on the already released model if you can. There are many ways you can share them, hubs, third-party libraries, or author release checkpoint. They have advantages and drawbacks. The main question is how deep you want to change the model, how deep you need to adapt the model for your target task. Because hubs provide you black box model that you can't really adapt a lot. And at the other end, auto-release checkpoints are kind of difficult to use usually because they are open sourced by researchers. We did our own library, which is called PyTorch Transformers. It was designed with two main principles, two strong principles in mind. The first one is to be as easy to use and as fast to onboard as possible. So it was made initially for researchers, but there's actually a lot of practitioners who use it because it's very easy. So you just instantiate a tokenizer which will convert words in indices, and then the model which take the indices and output these vectors, the identity vectors. So no abstraction to learn. And there is a simple command from pre-train method that will basically download the models that was pre-trained by Google or Facebook, or depending on which models you are using, or OpenAI, and take care of doing all of this. And the second stronger, so you can just then build upon it. If you want to make a complex model, you just add your head on top of it. These are simple PyTorch models for now, and now we're adapting it also for TensorFlow, so we have the two versions. And the second principle was that we wanted to have really state-of-the-art models. So as I was saying, like this transfer learning model, they're now topping all the leaderboards on all NLP tasks, pretty much all NLP tasks. And the model we provided in our library, they exactly reproduce this, reproduce the official results, so you can really trust them. So right now we have 8 models. The original one that made a lot of PR was BERT, released last year. GPT it actually was the predecessor of BERT, released by OpenAI in early 2018. GPT-2 made a lot of noise earlier this year because you want to release the full weights. It is also a very good model. Transformer XLNet is a Google model. XLM is a nice model if you're doing multilingual. It's available in 100 languages, which is really useful. There are only two models which are multilingual, which are BERT and XLM for now. I'm pushing for more because I think it's important to not have only English models, but yeah. Roberta is the current state-of-the-art on many language understanding tasks, and DistillBERT is something I'm going to talk a little bit later. It's our own model, which is a lot smaller. When you want to use this model, how does it look? It's quite easy. So you have your string. That's the nice thing about all these end-to-end models, that usually they just take this raw input, no pre-processing. You just tokenize it in a set of tokens. These are open vocabulary models. They are made to be run on the wild on like full any kind of internet inputs. So they have open vocabulary. So if the word is too complex, like Puppeteer, they will cut it in small parts that they know. And then you convert this in this number, which has this indices in vocabulary. You feed that in the transformer model that I showed you earlier. And this just output for each input, for each token, hidden states vectors, okay, which is the output of the model, the raw model. And then on top of that, usually you don't really want to have just this. You have a target task, and then on top of that, you usually have a classifier model, which can be just a linear layer projecting these vectors in just two numbers, right? Which is trained, so this part is trained on your target task. So here, for instance, this virtual target task is to estimate if this sentence is true or false, okay? So this part and this part are provided by our library, for instance. And this part is, well, we provided also this, but this part is usually what you train on your task, okay? This is how you use it. I wanted to put some code in my slides, even though I just have 20 minutes. It's very easy, so these are all these models. You just instantiate a tokenizer from a pre-trained checkpoint. Here, these are the name of the checkpoint. Usually, these models' architecture are various checkpoints which are more bigger or smaller or have more or less languages. For instance, this one are just English and French. So you instantiate the tokenizer on the model from these pre-trained models, and then you just input your sentence, tokenize it. You take your sentence, you tokenize it, you input in the model, and you have the vector. So it's like really dead easy to use in practice, right? This is actually all the thing you can do with the library. Just take one page. And we also took special attention to make this easy to use in production. So you can actually use star script if you know, or this kind of way to speed it up. I have to speed up also my talk. So just show you one complex task, which is language generation. This is a dialogue here, so you know we've been talking about dialogue for the whole day, so I won't really show you, but you usually have a knowledge base, you have a dialogue history, you receive a utterance, you want to answer something, okay? So it's a bit tricky because when we pre-train these models, we just have one input, like the Wikipedia articles they're trained on. But here we have a lot of context, we have a lot of inputs, various inputs. How do we combine them? There are many ways you can do that. We have an ACL paper that compare this. Basically, you can just concatenate all of them, which is the way I'm explaining. You would just put your knowledge base, your history, and the current reply you're generating in one sequence, and you input this sequence to your model. So it's also very easy to do. And you can do more smarter way to combine them by like duplicating the model and using the model for some inputs and another model for other inputs. If you want to check, we have an ACL paper on this. So yeah, so you can do more or less complex way to adapt this model. So this is to show you, but that's going to be a bit long, but to show you that it's very easy to use in practice. You just actually process the input, and the model, in our case, says the same. Now, if you want to use that in production, there is one problem, which is that this model, as I said, keeps getting bigger. So for instance, this Megatron LM doesn't even fit on 16 gigabytes of a GPU, so there is a problem, right? It's not really ready to be used in production. Another question is that these performance are getting, like the improvements are getting smaller as the models are bigger, but this is maybe not the main problem. So what we've tried to do at Hugging Face is to make smaller models. How can you do that? There is a smart way you can do that. Because you're usually okay to have a kind of heavy training cost because you do just the training once, but the inference cost in production is really where you want to have this as small as possible. So if you can use these large models, which are heavy to train, to make small inference models, that's cool, because you will capitalize on all the knowledge the large model will learn, and you will still have a small inference cost because you have reduced this large model in a smaller one. And we can do that. That's what we published this summer. You can keep, actually that's 97% now, we're even better, but you keep almost all the performance of a large model, and you can reduce the size of the model by at least 40%. Oh no. Yeah, I thought I had a way to explain a little bit about you, but that was too short to really dive it. So if you want to see how this works, you will have to check our blog post, sorry. Or you can ask me. I love to talk about distillation. Okay. So yeah, that was my quick talk on transfer learning and how you can try to use that in production.